All right, friends. So I mentioned something earlier that I said when you do the summation of the data like we just did, you lose specificity. You lose, for example, how many houses were at $100,000, how many A's, how many B's, how many C's. Basically, when you see a GPA of 3.55, that basically means that that student is doing, what's the closest thing to 3.55? 3.67, which would be an A minus, essentially, right? 3.55, if you're talking about that for a GPA. But that doesn't mean that the student got A minuses in every single class. But that's what an average means. An average says if he was to get the same grade in every single class, this is what that grade would be. There are probably a bunch of classes he got A's, and maybe a couple he got a B or a B minus, maybe even a C, depending on how many of each that he had. So you lose some of that specificity. So I want to go back to raw data for a moment and look at our friends Bert and Ernie from last week. We played with Bert and Ernie a little bit, right? A tiny little bit. What was the question I asked you about Bert and Ernie last week? Who was the better student? Who was the better student? What were our votes? What were our votes about Bert and Ernie? They're the same. All right, there's a vote that they're the same, and how come? Because we calculated that they're average. So we got Ernie. Let's come Ernie over here. Ernie's test average, I'm going to call it X bar, was is 81, correct? Yeah. Good. What was his median?
82. Oh,
good.
Ernie's.
Say that again?
Ernie's median was 81.
His is 81 as well? Okay, good. Did he have a mode?
No.
No, only 5 data points. Very often you don't. We did the trimmed mean as well. I think we lopped off the high and the low. So you lop off the low and the high. What's his trimmed mean?
81.
Good. So his trimmed mean is also 81, which tells us a little bit. It tells us that either number one, there are no unusually high or low values, i.e. outliers, or if there are, they're canceling each other in computation of the average. So basically he's at 81, no matter how we look at it via center. And Bert, let's look at Bert's statistics. How's Bert sitting? What's his average sitting at?
81.
81. What's his median sitting at?
82.
And what's his trimmed mean sitting at?
81.3.
Gotcha. So this is, I understand the latest vote. They're the same student. They're the same student when you view that statement through the eye of what? Through the idea of average, yes, Jen, through the idea of center. So, in other words, we have this beautiful thing called measures of center, which is fantastic. And that's what we've just been talking about. Quite a bit, actually. Means, medians, modes, what they imply. Let's come on over here real quick. So, the vote is that the students are exactly the same through the measures of center. Are they different in any way? Are they different in any way? They most definitely are.
The median's higher with...
Oh, right, David, you did say that. I remember you said that on Wednesday as well. The median is exactly 1 point higher. Although, if you stretch this, considering it's over 100 points, essentially that's essentially the same median. I see your point, though. I see your point.
But we can actually look not at the numbers, but just like how they were doing. One was pretty stable, another one was from like extremes.
So we got stability. Good, stability. Which one's stable?
Ernie.
So we're seeing as Ernie is more of a stable student. Let's put this back to the side.
Probably focused student.
Well, okay, now careful. We don't want to look at why these students
Okay.
got the grades, just at the grades they got. And we look at, and this is important to do. It's very easy to get attached to this and say that Ernie's, I think the fact that we say that Ernie's test scores are stable is a fair assessment. You look at them, and they're tightly clustered around that blue dotted line, which is the average. So if that's stable, we can use Bert to be unstable, because they seem to be more chaotically spread. Why they are is anybody's guess, because we don't know. I mean, maybe he was having bad days, good days, who knows, who knows.
Maybe he was sick.
Maybe Ernie is actually a 100 student, but had 5 really crappy days that he tested, and he just happened to test consistently crappy all those days. Crappy for him. I mean, not that an 80 or a B would be crappy, but there's all kinds of reasons as to why these students could fall there. But as far as just these 5 test scores, we've got basically, I like the idea of stability. I think one of you guys used the word consistency last week. We got more consistency in Ernie than we have in Bert. But you see, that difference, how many of you say Ernie's better because he's consistent? That's a fair thing to say. How many say Bert's better because he has the potential necessarily, maybe, to go out higher? Again, a fair thing to say as well. What we need a way to quantify that. That's the thing. We've got beautiful ways. We've got beautiful ways of quantifying the centers of these data sets. What we need now is a way to quantify the spread of these data sets. And that's what today starts talking about. Today, probably into Wednesday as well. Let me put the loitering screen up again. So I'm going to mute the screen for a second. Something, and this does not get taught very often. I mentioned before that very often in younger grades, students learn about averaging and medianing and moding, and we like that. The stepbrother or brother-in-law or sister-in-law of measures of center is what they call measures of variation. And there are lots and lots of words. Variation. And I'm going to put, you know what I'm going to do? Let's do measure the measures, the plural in parentheses. There's one in particular I want to play with in this class. There are a number of ways to measure or quantify variation. Only one of them gets used religiously in statistics, so we'll focus on that one. We'll focus on that one in class. So there's already some words you guys came up with. I love how, when you talked about center, one of the first things Rachel said today was she talked about the geographic middle. That was fantastic. I also heard balance. There's all kinds of other equal share. These are all words I remember from last week with you guys. I've already heard some good words for variation over here as well. Some of those good words are stability, stable, stability. Consistency. Or inconsistency. And actually, you know what? When we're talking about stability, instability. If something's unstable, or if it's got instability, it's going to have more variation than something that is stable. So is this consistency or inconsistency? Any other words kind of pop in to talk about that idea of variation? What are you guys thinking?
Group.
Say that again?
I don't know.
Grouped could or couldn't. It could or couldn't. So just, you're thinking clustered versus spread out. Yes. I gotcha. Clustered versus spread out. I'm sorry, I understand what you're saying. So like Ernie's clustered around his average, exactly. Bert's spread, clustered versus spread. Also, another word for spread sometimes is dispersed or dispersion. This is not an entirely intuitive kind of idea, which is why I like to spend some time going through it today. It'll take us hopefully until Wednesday to chit-chat about it. We don't want to rush through it today. So, I want to go back to the diagram of Bert and Ernie. And I want you guys to quantify, or attempt to quantify, without any prepping, how we can quantify Bert versus Ernie. So let me rehash what you've said so far. Ernie is more consistent. Love that. Ernie's more consistent. Fantastic. Bert's less consistent. Ernie clusters, Bert spreads out. How could we quantify it? What do you think? Give me some ideas of how we could actually assign a number. So in other words, Ernie's got this much variation. Bert's got this much. Any ideas? Any ideas at all? What do you think about go? What do you think? Go ahead. Be brave.
I don't know. I was saying measure. Like I was thinking like measure the jumps between.
I love that. Oh, but between like here to here, here to here, here to here. I like that. So what would that, as soon as you measure that, we now have a quantity, don't we? So what would Bert's quantity be compared to Ernie's?
Significantly higher.
Exactly, higher, significantly higher depending on how we define it. Love it. And that's part of it. We have to measure between these data points. The caution I give you is, well, here's one measure that is used, speaking of that. One that I'm not going to get too far into in this class is called the range, which is essentially where it is at the lowest to where it is at the highest. So Ernie has a very tight range from 79 to 83, so he's got a range of 4. Bert's is almost 40, almost 60 to 100. So Bert's 10 times the range that Ernie has. Now, I don't like to use the range very much, because if you just simply say that, in lieu of these data points, and you say Bert has 10 times the range as Ernie, would you necessarily get this picture in your mind? Potentially. But the problem with the range is, suppose Bert had 4 100s and a 60. He'd still have a range of 40. But I doubt very much we think he was as haphazardly random as he is right now. We probably think, oh goodness, he had one really bad day. But he still got a range of 40 because of the, and if we go back to our discussion about a GPA getting hammered by one bad term. So the range, you've hit the range on the head, Robin, and it is used. We'll use it intermittently through the course, but I don't want to focus on it for something that we're going to talk about in 244 a lot more, which is the idea of unbiased estimation. But you've hit it nail on the head. Go with the idea that Robin started, though. We have to measure each individual data point, but not as they compare to each other. Not as we compare to each other. I want to come over to this side of the board for a second and give you kind of an idea of what to think. When we talk about variation, it implies, at least we're going to make it imply in this class. And then once you understand how it implies in this class, you'll be able to take it to anything else. We're going to be talking about variation from the average or mean. Or mean, which is the same thing. And I'm not sure what your textbook says. It might say average, it might say mean, they're the same thing. So basically, what we need to do is we need a quantifiable way to take Robin's idea of the spread of the data, but talk about the spread of the data with respect to the average that we just got done carefully crafting. Not the median and not the mode. The standard deviation, or the deviation we're going to be talking about today, the variation we're talking about today, is going to be measured from the average, from the sample average. Okay, now this is, I'm not saying this is the only way to measure variation. I'm saying it's the most common way, which is why I want to focus on it. I can fill your heads with like 5 or 6 different ways to measure variation. That's kind of dumb. It makes more sense to focus on one that gets used all the time, and then once you understand that one, the other ones will fall into place if you need them later on. So how can we quantify that idea? How much the data deviates from the mean? For example, let's look at Ernie, just Ernie for a second. What's that test score right there? That's 79, right? 75, 76, 78, 76. How does that data point deviate from the mean? And the mean is the blue dotted line. I added up there. Well, go ahead, Jen. It's 2 points below, correct? 2 points away. In this case, 2 points below. And the reason I specify that is, how does 83 deviate from the mean? It's also 2-point deviation. It's 2 points above. Now, Jen, I love what you just said. She just put her fingers up 2. Perfect. It is 2. There is a measure of variation that does not care whether it's above or below. It's called the average deviation. So in other words, to the average deviation, the 79 and the 81 look the same because they're 2 points away. But nobody uses the average deviation. I shouldn't say nobody. I'm sure somebody uses it. It's in Excel as a function, which means somebody uses it somewhere. But statisticians don't use it. And since we're trying to teach you guys to be like little micro-statisticians, we're going to ignore it too. So we need a way to talk about the deviation not just in magnitude, but also direction. Are those words okay to use? So the magnitude being how far away, and the direction being which way, up or down from average. Is that fair? Good, good. So, do we have our magnitudes and our directions? How does 79 deviate? To the left. 2. Direction to the left. 2 in magnitude. How about 80? To the left, 1. How about 81? No deviation at all. Same as the average. How about 82? It's to the right by 1. How about 83? To the right by 2. Beautiful. So, let's quantify. How much is Ernie varying from his average? What do you think? If you had to turn all those values, -2, +2, -1, 1, 0. If you had to turn all those things into a quantifiable one single value to describe his deviation, what number would you use? Say that again.
2.
I vote for 2. Why 2? Just out of curiosity.
I don't know.
Because it's the, go ahead, Robin, be brave. This is, you don't have the answer to this. I'm trying to push you to give me what you think is a gut feeling, because it'll give me, hopefully, a better way to explain it by hearing your guts. Go ahead.
Maybe like -2, +2.
Okay, so what you've just done, Haley, I want you to hold that thought for 48-ish hours. Maybe 47. No. What Haley has just given us, did you hear what she said? It was what was awesome. She said because the variation goes from -2 to +2. So in other words, all the variation that we see in the data set is at the extreme, -2, at the most extreme, +2. You've just described what's called a confidence interval, which is related to this idea, but not the idea itself. If you would, 47 hours-ish, plus or minus.
Okay.
Speaking of a confidence interval, plus or minus, it's an awesome idea. But I want to make it even more specific. What you've done is given us a range of all possible values. I want one value in particular. So hold that thought. I love it. You're about 2 days ahead of us. Jordan.
Would it be 0 because adding everything together equals 0?
Here's the problem. When you look at the distances from Ernie, each data score to the average, if you're averaging, it sounds like you're trying to average of Jordan. So you're saying -2, -1, 0, 1, and 2. If you try to average those, that's one idea, right? Is just to average those deviations. The problem is they add up to 0. -2 cancels +2. If you look at Bert, the same thing happens. If you look at Bert, the exact same thing happens. 61 from 81 is -20, correct? Let me keep this over here, -20. How about 68 to 81? Is that -13? 13, not 31. 82 to 81? 94 to 81? That's a +13, isn't it? And then 100 to 81, +19. Sum to 0. Here's the problem. They always will sum to 0, no matter what your data set is. Now you know intuitively why that is the case. Remember what we talked about? What word do we use to talk about averages? What word? Did it with my finger earlier on the scale. It's balance. It's where you have to put your finger to balance the scale. Well, wouldn't the positives and negatives have to cancel each other for it to balance? That's a problem. Well, it's a problem for this. It's a problem for measuring variation, which is that it comes back full circle to our problem with measuring Bert and Ernie. They both have the same balance point, even though Bert's weights, if you will, are spread way out compared to Ernie's very tightly clustered weights. So I propose a more analytical solution. Just a little tiny bit of algebra, if it's okay with you guys, or at least algebraic symbols. Algebraic symbols. Jordan, you've taken us down a nice path. I like where you've gone with us. So what Jordan has done is, he's listed out Ernie's, let's do Ernie's first. We're going to calculate Ernie's deviation by hand. Okay? So this is going to be his, this is just Ernie. Get rid of this, because that's Bert. Here are Ernie's test scores. 79, 80, 81, 82, and 83. You guys figured out very quickly, very quickly, what this statement means. Variation from the average, or mean. You figured out very quickly what that means is take each one of those data points and subtract off the average to see how far away it is. Very quickly you figured that out. So 79 minus that 81 gives you -2. 80 minus the 81 gives you -1. That gives you 0 because it's right there. 82 minus 81 gives you 1, and 83 minus 81 gives you, gives you 2. Those are the deviations. -1, -2, 0, 1, and 2. Bert's deviations, -13, whatever they were, 19, -19, +20, I forget what they are now. The problem is, no matter what data set you start with, and no matter what average it has, this will always be true. The summation of those deviations is always going to be 0. That's a problem. It's a problem because it would be nice. It would be nice to just simply take these numbers and average them. Because that would be simple, because we already have the measure of an average. And it wouldn't even have to be a weighted average, because the data's raw. Count each one time. So this one's 2 down, this one's 2 up, this one's 1 down, this one's 1 up, and so forth and so on. Beautiful! Problem is, no matter what your data set, that's always true. As a matter of fact, for this homework set, which won't be due till next Monday, I have an extra credit problem, is to prove this algebraically for any data set. This always works. Now we just saw it for 2 specific data sets, Bert and Ernie's. You can prove it algebraically using basically algebraic symbols to prove that has to sum to 0 for any data set. It's tricky because it's algebra, and it's tricky algebra. But so by all means, give it a whirl if you want to.
Yeah.
But rather than focusing on why it works, because you can focus on for extra credit, I want to focus on how to fix the problem. How to fix the problem. How can we still measure this variation when this column sums to 0? Because that's an issue. So Jen, you already gave us one of them. Unfortunately, nobody ever uses your solution. Jen's solution was take the absolute value. Ignore the negatives. -2 is just 2 down, but forget the fact that it's down, just call it 2. That, if you did that, the sum would no longer be 0, would it? It would sum up 6. 6 divided by 5, 1.2. Yay, the variation is 1.2. The problem is nobody uses that. It's called average deviation. The one that folks use is called standard deviation. And we're going to build it right here to show you what's actually going on with it. And there's a reason standard deviation takes preference over average deviation. We'll get to it a lot in this class, a lot more in 244, more at a rigorous level. But here's the way you can avoid this summation to 0 issue with the x minus x bars. Rather than taking the absolute value, take what appears to be a more destructive result and square the deviations. Square the deviations. This is a problem because you're squaring things. And the further those values get away from 0, the more the squaring is going to exponentially make that. We'll deal with that. We'll deal with that. So -2 squared gives us 4. -1 squared gives us 1. 0 squared gives us 0, 1, and 4. So Jim, we're kind of getting your idea, but we're getting kind of a bastardized version of it, in that we're squaring the deviation. So we're losing the negatives. We're losing the negatives, but now we've got these, and we'll deal with that by taking a square root later. We'll undo the squaring momentarily. When you add this up, friends, when you add this column up, I want to use the symbols if it's okay with you guys. The big sigma of x minus x bar, which simply means sum up this column, you end up with 10. Now, what that is it's the sum of the squared deviations from mean. Very often, if you read research journals, you'll see SS for sum of squares. That's what they're talking about. That's the value they're giving you right there, is the sum of the squared deviations. I don't like stopping here. Because the problem with that is whatever unit was on the original data has now been squared. So in other words, this is 10 square points. I don't know what the hell a square point is. If your original data was dollars, this would be square dollars. If your original was inches, it would be square inches. Now square dollars is stupid because it doesn't mean anything. Square inches does mean something. It means area versus a straight line. That's confusing. So I don't like stopping here. I do want to talk about this. And I want to average this. Because now I've got, this is the overall data set's deviation, right? All 5 data points added together. This is probably the most confusing part of this measurement of variation we're about to do. Bear with a couple of vocabulary words, if you will, with me right now. We're going to calculate something called the sample variance first. The sample variance. And this is the one and only time you'll do these 2 calculations by hand. One and only time you'll do it by hand, I promise you. Because it gets tedious. And you can imagine with a data set with many, many values, and this would suck. And it would be terrible. The sample variance is found by taking that sum of squares that you just did. Don't you dare memorize this formula, by the way. Don't you memorize this formula. I mean, we're going to calculate it right now, so you need to use it, but don't try to commit it to memory. Just realize what this is how it's defined to be. This is a human being's definition of how we're going to measure this variance. So you're going to take that sum of square deviations, which is over the entire data set, and you're going to divide it. Now you'd think if you were averaging, you would divide by how many data points there are. But in a cool twist of algebra, it's actually divided by n minus 1. Which, exactly, Rachel. She looks at me, she's like, wait a minute, I was with you right up until that point. I was totally with you. It's a cool twist of algebra. It's not going to make a whole lot of sense right now. And I apologize for that. There's a much, much better explanation that will reveal itself as we go through the class. But there's a mathematical reason as to why you have to do this. It has something to do with what's called an unbiased estimator, which doesn't make any sense right now. So if you would, this is one of the 2 times in this class I say, bear with me. You'll understand why as we go through. I've tried to front-load explain this in the class at this point, and it just confuses people even more. So bear with me, realizing you'll never have to use this formula by hand again, and the answer that you get logically makes sense without the formula. So just bear with me. I always get at least one of those like, okay, cool, 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 not cool rule, not cool at all. Totally get it. I'm used to it. 15 years of seeing it now. I would be surprised if I didn't see it. Oh yes, n minus 1 makes perfect sense. That's what I